So just to define a rational function, it's a quotient or ratio of two polynomials. So a quotient or ratio of two polynomials. And if you think about the parent graph for a rational function, it looks like this. It has a couple branches, and it has a couple of asymptotes too, horizontal and vertical. The big little concept is a way to kind of start to think about a calculus idea called the limit. And the idea is if you have a constant term over something that's growing really fast, something that gets big really fast, then this is going to equal 0. For example, if I have 1 divided by, say, x squared, or even 1 divided by x, as x gets really large, this whole term will get really small. It's like, think about the bottom of this, as the bottom of this fraction as it goes from 1 to 2 to 3 to 4 to 5. Now we're at 1/5 and then 1/10 and then 1/100. It's getting closer to 0. You can see that in the graph over here. As x gets bigger, the y value gets closer to 0. Whereas if you have 1 over a little, like if you have 1 over something that gets smaller and smaller, for example, 1 over 1 is 1, 1 over 1/2 would be 2, 1 over 1/4 would be 4, 1 over 1/8 would be 8. As this gets smaller, this approaches infinity. So as it gets smaller, closer to 0, that gets closer to infinity. So that's the big little concept. And it's just embarking on the idea of a limit. Okay. So vertical asymptotes. Says we have a vertical asymptote at the line x equals c if c is a 0 of the denominator. So in other words, we have a vertical asymptote if it makes the bottom 0. But c is not a 0 of the numerator. We actually call that, if c is a 0 of the denominator and the numerator, we call that a removable discontinuity calculus. So it has to be something that cannot be canceled with a factor in the top. So c is a 0 of the denominator, but that same value c is not a 0 of the numerator to be a vertical asymptote. If perhaps last year you guys looked at like holes in graphs, how you'd end up with a hole. Did you look at those at all? We're going to look at that this year. You end up with a vertical asymptote if you can't cancel out the factor in the bottom. You end up with a hole if you can cancel it out. And it's just a single point. It's a hole in the graph. So we'll look at that this year. All right. So let's find the vertical asymptotes of the following. Oh boy. I'm struggling. So let's find the vertical asymptotes of these next 3 functions. We're going to go ahead and do that right now. And so the first one. To find vertical asymptotes, we're going to set x squared minus 4 equal to 0. So set x squared minus 4 equal to 0. And then factor it to find the zeros. So we're going to find the values c that make the 0. So, or just solve it. So if I solve this, what do I get as my zeros? Plus or minus 2. Now, are either plus or minus 2 also a 0 of the top? No. The only 0 on the top is 0. So that means the vertical asymptotes are x equals 2 or x equals negative 2. Those are my vertical asymptotes. So those would be the vertical lines that the graph of this rational function never crosses. Okay. It might be worthwhile to look at to see what this looks like. I'll show you. What about b here? If we solve x squared plus 1 equals 0, we get x equals plus or minus I. What does that mean? That means there are no real zeros, so there is no vertical asymptote. Let me show you the graph of this one. So no real zeros, therefore no vertical asymptote on that one. Let's look at the graph of this place. So it's y equals x to the second, and on the bottom it's x squared plus 1, and let's graph it. It's like a seagull's wings there. But what's happening on this one is we have no vertical asymptotes. No vertical asymptotes. At one point it hits the origin here and then bounces off of it. Okay. That one has no vertical asymptotes. And then C, if g of x equals a quadratic over a cubic. So here's what needs to happen on this one. Let me show you just a quick graph so we know what to expect. And then we're going to go ahead and use our techniques that we've been learning to factor both of these. Geometer's Sketchpad is a little better job of handling vertical asymptotes than, as well as holes than your graphing calculator. So I can get a picture of this quickly. Okay, so right here you'll see this function. We have a vertical asymptote that looks like right here at about maybe -7. And there's another, looks like vertical asymptote possibly right here at 0. You can see there's 2 branches, and then right here kind of a parabola looking thing. Let's go ahead and factor this. So can you factor the top? What are factors of -2 that add equal 1? -1 and +2. And then on the bottom, how can we factor the bottom? Do you see a common factor there? What's common to each one of these? Looks like x could come outside of x. I'm left with x squared plus 9x plus 14. And then can I factor the bottom further? Factors of 14 that add equal 9. Yes, I'm going to 2. So this is an example of one that has some zeros in the denominator, but one of them is also a 0 in the numerator. So if you look at this right here, the x plus 2 factor, that can cancel out top and bottom. And so the vertical asymptotes are only those zeros that are not also zeros in the top. Or another way to say that is any of the zeros in the bottom that don't get canceled out with factors in the top. Okay. So the vertical asymptotes on this one are x equals 0 or x equals -7. x equals -2 is not a vertical asymptote because it gets canceled out here. So you might want to make a note of that. So is not a vertical asymptote because it is a 0 on top. Or another way to say it is because it factors out. It's what we call in calculus a removable discontinuity. So looking back at the geometry sketch pad, I'm going to show you something here. And then we'll come back to this so you can finish copying it down. So at negative x equals -2. Right. So if it's a 0 in the bottom and also a 0 in the top, then it's not a vertical asymptote. It's what we call a hole. All right. Move all this stuff over. Horizontal asymptotes. These should be new for you. I think you probably haven't talked much about them. Vertical asymptotes, the graph won't cross over them. Horizontal asymptotes, it can. The graph can cross over horizontal asymptotes. Here's the definition of a horizontal asymptote. It says, if the degree of the numerator is less than the degree of the denominator, kind of like this part A up here, then the x-axis is a horizontal asymptote. In other words, we have a horizontal asymptote at y equals 0. Okay? So that's what we saw in this first graph right over here. Is if the degree of the numerator, which is 1 in this case, is less than the degree of the denominator, which is 2, then we have a horizontal asymptote at 0. The reason for that is that concept of the 1 over a bigger number. In other words, if I were to think of this as in terms of as x gets really large, this -4 makes no difference. If I take infinity and square it, right, I have infinity. If I subtract 4 from it, it makes no difference, really. So what this amounts to is just 1 over x. Okay? This isn't canceling that you can do unless you're talking about infinity. But when I think about x being really big, the -4 makes no difference. And so if I just look at just the leading coefficients, it's 1 over x. And so as x gets really big, it falls into the 1 over big idea, and it goes to 0. Let me just show you real quickly here that graph again. All right. If the degree of the numerator equals the degree of the denominator, then the ratio of the leading coefficients is a horizontal asymptote. So here's what we mean by that. Let's write that down and I'll show you. B up above is a perfect example of that. The degree of the numerator on B is 2, and the degree of the denominator is also 2. So if you look at the coefficients here in front of the x squareds, what would this reduce to? 1. So it's 1x squared over 1x squared, so it'd just be 1. So we expect the horizontal asymptote here to be 1. Okay, so let's graph that guy. Back over here, let's go ahead and graph this guy again at second insert squared and then x squared plus 1. And we'll graph it. And you can see it, kind of see here. It looks like it lands right on 1, but or y equals 1 is a horizontal asymptote. You can see it as x gets really big, it just locks in at y equals 1 there. Same thing as x gets really small, it goes to negative infinity. So this one doesn't have a vertical asymptote, but it does have a horizontal. Okay? So there's one more case here. Here's the degree of the numerator is less than the denominator. Here's the degree of the numerator is equal to. What do you think happens if the degree of the numerator is greater than the degree of the denominator? What's that? It's a good guess, yeah. So if it's big over something small, it's just it's like this right here. Or 1 over little, if you will. Where does that go to? And so infinity is not a specific number. So the third case here, which we're going to talk about later, if the degree of the numerator is greater than the denominator, then it has no horizontal asymptote. It just takes off to infinity, yeah.
And if it has no horizontal asymptote, would it have to have a vertical asymptote?
If it has no horizontal asymptote, would it have to have a vertical asymptote? Good question. If it doesn't have a horizontal asymptote here, the degree of the numerator is bigger than the degree of the denominator, then it is going to take off to infinity. In terms of it, it could just keep on going. I can't think of an example where it would, but it wouldn't necessarily have to have a vertical asymptote there. Trying to think of an example where that would be the case. Let's look at our examples. So we have this one right here, A. Which category does this fall into, number 1 or 2? 2. The degree of the numerator and denominator are the same. Okay. So what's the horizontal asymptote going to be? Yes, the horizontal asymptote will be, and horizontal asymptote is always a y equals line. It's going to be y equals 1 over 2, and that's it. If the degrees are the same, it's the ratio of the leading coefficients reduced. Okay, that's it. So if I were to graph that, y equals 1/2 would be a horizontal asymptote. Now, what a lot of students think is that a lot of students come in thinking the same way about horizontal asymptotes as they do vertical, that it doesn't ever cross it. That's not true. It could cross it multiple times. What it means to be a horizontal asymptote is that way out to the right, it looks like the horizontal line y equals 1/2. The graph eventually hones in on y equals 1/2 and just stays near it. Okay. If this is the only horizontal asymptote, it means the same thing as x goes to negative infinity, that it just hones in on that and stays near it. Okay, but it can cross it multiple times. What about B? Which category does B fall into? First. So that means the horizontal asymptote is y equals 0. Okay. So vertical asymptotes are when you have something in the bottom that cannot be canceled out. Okay. Whatever makes the bottom 0 that cannot be canceled out is a vertical asymptote. Horizontal asymptotes are when you have the degree top and bottom are the same. It's the ratio of the leading coefficients. If the top is less than the bottom, then it's y equals 0. And if this was switched around, then there'd be no horizontal asymptote. Okay, that's it. Last type of asymptotes, you probably didn't look at these last year. These are oblique asymptotes. Oblique asymptotes. Is this a new term? Oblique asymptote. It's if the degree of the numerator is 1 bigger than the denominator, then the numerator divided by the denominator is an oblique asymptote. I can show you what I mean by that. Let's find the oblique asymptote here on number 3. Might be helpful. Let me show you what it looks like for. So the instructions here are to find the vertical and oblique asymptotes of the functions here. So number 3, just find the vertical asymptote. So what's the vertical asymptote here? Just real quickly. Might help to factor out. So the top factors is x minus 2, x plus 1. We need to factor out the top, I guess, just to see that it doesn't cancel with the bottom. So what's the vertical asymptote then?
X plus 5.
Yeah, x equals positive 5, that's right. And then the oblique asymptote. By the way, does this one have a horizontal asymptote? No, because the degree of the top is bigger than the bottom, so it does not have one. But the oblique asymptote is going to be whatever I get when I go ahead and divide the bottom into the top and ignore the remainder. Okay, remember I said ignore the remainder. So can I do the division here? Let's do it synthetically. 5 into 1, negative 1, negative 2. We're going to have a linear function. So bring down the 1. So ignore the remainder. What does this give me as an equation?
X plus 4.
Because I divided a first degree into second degree, what's left here is a first degree. So my oblique asymptote is y equals x plus 4. That's it. All right, so let's put it all together for these last two, and then I'll have you try some in groups here. So let's put it all together. It says on 4, find all asymptotes. Okay. So let's start with factoring this. Do you know how to factor difference of cubes? And let me write down the formula. It's a cubed minus b cubed equals the cube root of each, matching the sign, times the first term squared times the two terms in the parentheses and opposite sign plus second term squared. So that's the formula for a cubed minus b cubed. It's take the cube root of each, that's one of your factors, and then square the first term, take the product of the two cubed roots, and then plus the second cubed root squared. So what's the cubed root of x cubed? X. And the cubed root of 8? So it's x minus 2. And then if this is your a and your b, then this will be x squared plus, if this is your a and your b, you multiply them together, you get the middle term. And then if this is my b, 2 squared will be 4. And what are the factors at the bottom now? Factors of 6 that add to equal negative 5. Yeah, negative 3 and negative 2. So x minus 2, x minus 3. Good. Okay, so from this factored form, see how this connects to what we've been doing? We've been learning how to factor all these different polynomials, even third degree, fourth degree. So you got to factor it first. But from factored form, then I can tell what my vertical asymptotes are. From the original form, I can tell what the horizontal asymptotes are. Let's do that first. What's the horizontal asymptote here? There isn't one, so none. Good. Good. Because the degree of the top is bigger than the degree of the bottom. What about vertical asymptotes here? Do I have any vertical asymptotes? Notice the x minus 2 cancels out. Okay. So 2 is not a vertical asymptote, but this one I can't get rid of. So for that reason, x equals 3 is a vertical asymptote. What about oblique asymptote? Am I going to have one of those in this case? Yep, the degree of the top is 1 more than the degree of the bottom. Now, here's the problem. I've got to do some long division. Now, I can long divide the original, or I can do synthetic division with what's left over. Do you see that here? So let's do that. Yeah, that would probably be the smarter thing. I've already divided the x minus 2's out. Now, if you couldn't do that, you'd have to go and do long division with this. Okay. But I can take 3 into 1, 2, 4. Let's see what happens. And so what is my oblique asymptote based on my long division or synthetic division here? Y equals x plus 5. Right? Okay. Y equals x plus 5. Ignore the remainder. What you're ending up with is this linear function is what this graph would approach as x goes to infinity. Okay. So do the long division. So horizontal asymptote, you're going to have to memorize a couple things there. Okay. There's basically 3 cases. Either the degree on top is higher than the bottom and there's no horizontal asymptote, or they're equal, in which case it's the ratio of the leading coefficients, or the degree of the top is smaller than the degree of the bottom, meaning 0. Vertical asymptotes you've already studied before. It's whatever makes the bottom 0 that can't get canceled out. And then oblique asymptote, you got to have degree on top is 1 more than the degree on bottom. Do the division, and then whatever pops out here is your oblique asymptote, okay? What about B here? Let's just first of all identify the horizontal asymptote. Before we even factor, we can identify it. What is it? Look at the leading coefficients, reduce it, and we're done, right? 2/3. Before I can find the vertical asymptote, I got to write this in factored form. So here we go. I think this can factor. 2x squared minus 5x minus 12. Probably going to be 2x and x. Minus 4 plus 3, is that it? Minus 8 plus 3, yep. What about the bottom? I bet it's 3x and x. Maybe minus 4 plus 1, does that work? Negative 12 plus 1, yep. So now I have it in factored form. I see that this cancels out. So what is my vertical asymptote? You tell what the vertical asymptote is just by looking at this right here. What would make this 0? Yes. And then what about the oblique asymptote? Do we have an oblique? No, there's none. Because degree of top is not 1 more than the bottom. Okay? So because the degree of the top is not 1 more than the degree of the bottom, then no oblique. Okay? That's it. So obliques, and this is probably some new stuff with obliques and horizontal.